This screencast is on electrostatics, and it will concentrate on charges and forces that exist between charges. So we start with the fact that all objects are made of atoms. Atoms will have positive and negative charges. When a material has an excess of negative charges, it's a negatively charged object. If it has a lack of negative charges, it would be a positively charged object. Now, as far as charged objects go, there's some rules that you've probably picked up along the way. And first, opposites attract, and like charged objects will repel, and that a neutral object, when brought nearby a charged object, will be attracted to the charged object, regardless whether it's positive or negative. Now, here are some of the theories that have developed over time about the atom, and the one closest to what we use now is Bohr's model. And in Bohr's model, we have a nucleus. It's a tightly packed area. In this tightly packed area, we have neutrons and protons. And the neutrons act sort of like the glue that keeps the protons together. Protons repel each other with great force, and it's hard to keep them together in such a tight place. So we need a nuclear force to keep them together. Now, orbiting around, we have our electrons. Now, electrons are really, really far away. There is a lot of space here. I can't really put it on the screen because it wouldn't really fit, but if we want to set it up to some kind of proportion, if our nucleus here was the size of the tip of your pencil, then our electron would be about 1/2000th of the size, or 1/4000th of the size of that nucleus. So it would be a tiny, tiny little speck on your pencil. Couldn't even see it. And its first orbit would be about 3 blocks away. So there's a lot of empty space that we have here. Because of that, electrons are the ones that is more easily gained and lost. Protons are pretty tightly packed in this nucleus. When protons leave, it's usually a big deal. We're talking nuclear reactions. Electrons leave, not really much of a deal. Now, when an object gains or loses an electron, we say it becomes an ion. Like that. Now, charges aren't created or destroyed. They come from somewhere and they go somewhere else. They're always conserved. And so we have the law of conservation of charge. Now, some materials will allow these electrons to flow quite easily. Those are called conductors. And good conductors can be things like copper and gold and so on. Insulators are materials that do not allow electrons to transfer quite easily. So while conductors will easily gain an electron and give up an electron and easily allow an electron to transfer its way down, insulators not so much. They hold on to their electrons pretty tightly. They don't gain or lose that easily, and so when charges are placed on an insulator, they don't tend to move around very much. Now, a few terms you have to be familiar with. First one is conduction, and conduction happens when you have a metal object and electrons are able to transfer and move along the metal object. That's called conduction. Conduction can be for electricity, that you conduct using a wire from one battery to a light bulb or something. It could be from heat. If you hold a spoon over an oven and the spoon gets hot and it reaches up into your hand, those are examples of conduction. Induction is a little bit more interesting. Induction refers to a movement of charge. So if I have let's say a neutrally charged object here, and if I bring a charged object nearby, so let's just say this object is very negative, the protons won't move around because they're stuck in the nucleus, but some of the electrons, they will feel repulsion from these electrons and they will move, all try to move away to the other side. And so what you'll find is you'll have an object that is positive on one side and negative on the other side. And so the reason positive or negative objects attract neutral objects is from induction. We have our electrons move around, so now all of a sudden this positive side is attracted to the negative side and the two objects attract. But notice that the same amount of charges exist. You haven't gained or lost charges. And when you move away or you remove this negative object, then all the electrons will come back to where they were. So that is an example of induction. So now, speaking of charges, we'll look at the elementary charge. Both an electron and a proton will have the same charge, and it is an elementary charge of 1.6 times 10 to the negative 19 coulombs. The difference is a proton will have a positive charge, the electron a negative charge. Now, what interesting thing to note is that the proton is much larger than electron. It's about 1,000 times larger, and so it will have a lot more mass, but the strength of the charge will be the same as a proton electron. If we want to find out how much charge an object has, what we can usually find is the excess electrons, which would be n, times elementary charge, which is 1.6 times 10 to the negative 19, and this will give us the charge of the object. Now this could be for electrons or protons. Now the next thing we look at comes from a French physicist, and it is the force between charges, and it's referred to as Coulomb's law. Now Coulomb's law is F equals kq1 q2 over r squared. Now if you notice, it kind of looks like something else that we've done before. Similar pattern, but there's a really big difference. When gravity, everything attracted with force, things can attract and repel depending on the charges. Now what I usually ask is, when you're doing these questions, to actually not put the sign inside, to just put the magnitude, and after you looked at it and you have an answer, then decide what's going to happen. Are they going to repel or are they going to attract? So in the first case, we know that the force of A on B means that B will be pushed away. There's a force going to the right. For the other one, B is attracting the negative charge, A on B. So in this case, it's going to be a force to the left. Now, just like gravitational law, we had a constant. For Coulomb's law, our constant is 9 times 10 to the 9 Newton meters squared per Coulomb squared. Alright, so now I have an example here where I have three charges. 25 nanocoulomb is 0.001 meters away from B, which is negative 17 nanocoulombs, and that's 0.002 meters away from the 22 nanocoulombs. So what I want to find out is, what is the force on B? Now I'm not going to use negative and positive signs in my equations. I'm going to take a look at directions. And I know that from A on B, it will attract force B. So F of A on B will be going left. And then the force of C on B will be attracting it this way. So now I need to calculate the magnitude for each one. So to find out the net force on B, then I will find out the force of A on B, and notice I don't use a negative sign, and so the force of A on B is going to the left. Then to find out the force of C on B, and that will be K, Q, C, QB over R squared. 9 times 10 to the 9 times 22 times 10 to the negative 9 coulombs. And this works out to 0.8415 newtons going to the right. So what I need now is my net force, and I'm going to go with my bigger number, which is going left. So I predict this will be going left after. 3.825 minus 0.845 newtons is equal to 2.98 newtons going to the left. And that is the net force on charge B. Now the last example that we'll do will be a little bit trickier, and it still comes down to the basics of forces, and we have a formula for force. But again, like the previous example, there's actually two forces. But this case, this is going to be a vector problem because it's not just linear. We see that we have three charges here, and they are making sort of the, I guess like a triangle. We have positive 5 microcoulombs, and then we have positive 8 microcoulombs, and then positive 12 microcoulombs. So one thing that is different is they are all positive, and that will also require a vector addition to solve this. So we have a quick look, and if we want to find the force on B, we see that C on B is going to exert a force this way. It's going to be pushing away, force of C on B going that way. And then if this is, I'm not sure what happened to my letter A, there we go. If this is A on B, then it's going to exert a force going that way, A on B. So what we're going to end up with is two vectors, and we'll have to add them head to tail, where F of C on B plus F of A and B will give us a net force going that way. And so the result of these 5 microcoulomb charges and the 12 microcoulomb charge is that it will end up pushing the charge somehow that way. So back to basics here. We're going to start with just forces. What is the force of A on B? So force of A on B will be K Q of A Q of B over R squared equals remember microcoulomb is times 10 to the negative 6. So, the force of A on B exerts a force of 14,400 newtons going downward. So the force of C on B will be K QC QB squared. And now the distance from C to B is 0.007 meters. And that works out to 17,633 newtons. Okay, so we have our two forces, so we're going to add this head to tail here. I'll say this is 14,400 newtons going down, plus 17,633 newtons going horizontally. Maybe let me redraw that so it's a little straighter. And then that will be our result. And that will be the net force acting on that charge. So this will be a right angle triangle with an angle which we'll need later. So since this is a right angle triangle, I can use Pythagorean theorem, say F net squared is equal to one side squared plus and we solve for the net force of 22,766 newtons, and we are going to need an angle here. So if I have my angle, this will be my opposite side, this will be my adjacent side, so we're going to be using tangent for this. And so to find my angle is going to be inverse tangent of my opposite, which is this, over my adjacent, which is this, which gives me 50.8 degrees, and that is west of south, the way I've set it up. And so I'm going to rewrite the statement and say my net force is 22,800 newtons. So using pre-sequence digits, and maybe I'll use a smaller angle and call this 39.2 degrees south of west. Okay, so make sure you've read over the notes on forces and charges and try some practice problems and see if you can get it to work out.